Today we're going to continue our discussion of divisors in particular. We're going to look today at the greatest common divisor, and then next class we'll talk about least common multiples. And to start with, greatest common divisor, also is sometimes called greatest common factor, is the greatest whole number that divides all the numbers in your set. It might be worth writing yourself a note that this cannot be bigger than the numbers in your set. So while it's called a greatest common divisor, it's actually smaller usually than what you're working with. Okay, so these numbers are smaller numbers than what you start with. We've actually talked about the next definition, but I haven't used the words. The words are relatively prime. Relatively prime are two numbers whose GCD, their greatest common divisor, is 1. Or you could say they have no factors except for 1 in common. And we saw that back when we did divisibility rules, the questions you were just asking, that Maddie just asked us about the number 12, being able to break them down into 3 and 4 or 2 and 6, right? 3 and 4 are relatively prime. It doesn't mean they're prime, it just means they have nothing in common. Nothing besides 1, okay? 6 and 2 are not relatively prime because they can both be divided by 2. Everybody with me? So the reason that 3 and 4 worked was because they were relatively prime. There are lots of methods for finding out what the greatest common divisor is for two numbers. There's a common one that you've probably done more than the rest, but I'm going to show you several methods, and they would be at different age levels of appropriateness. The first one would be for our youngest groups of children that are talking about this kind of topic, and this is called the intersection of sets method. In this method, you would list all the divisors of each value, and you'd find the biggest one. As long as the numbers are small, this is not difficult to do. Right? If I want to write down all the factors of, factors or divisors of 20, we could do that, and we could do it pretty quickly. But if I wanted to write down all the factors or divisors of 20,000, that's a different conversation. Okay? So there are definitely numbers for which this is, usable, and numbers for which it's not very usable. And we're going to do one that's really small, because this is where you would actually see it used. The numbers 12 and 15. Okay? So what we're going to do is we're going to start with the number 12, and we're going to list all the factors. Now, we talked last time about factors coming in pairs, so that's useful to us. Don't forget the pair that's 1 times 12, because it could be that you're working with numbers where one of those is actually the greatest common factor, okay, greatest common divisor. If we go from if we go from 1 times 12 up, what would be the next factor besides 1 that divides 12? 2. And that would be 2 times 6. What else would we have? 3 times 4. And if we do this in a organized way, at some point we realize that we get to a point where there aren't any numbers between 3 and 4, so we're nowhere done. Now, I know this particular one you knew you were done anyway because the numbers were small, but even if the numbers are larger, as long as you're working your way up, down the side over here, right, 1, 2, 3, or whatever happens, it's increasing. The other side will be decreasing, and this point where you get to in the bottom is going to have the numbers so close together, there's just no other options left between them. Does that make sense? Okay, cool. So what we're going to do next, let me clear off all those markings because they're not useful, really. And we're going to do the 15 the same way. So I'm going to start with 1 times 15. What else? 3 times 5. And again, when I get to 3 times 5, the only number between those would be 4, and that's not going to work at all, right? Yeah. So what we're doing then is we're going to consider these two lists, And we're going to find the biggest number that's present in both lists, and that would be what? It would be 3. So the greatest common divisor, or greatest common factor, would be 3. That's it. Okay? Again, it's pretty quick and easy as long as the numbers are fairly small. It becomes a little bit more cumbersome if the numbers get larger. The next method is probably one that you've seen done a lot. It's the most common one, as far as I know anyway, in terms of textbooks, and it's called the prime factorization method. This method, what you do is you construct the prime factorization for each number, just like we were doing back in section 4.2. And then every prime factor you list, for every prime number in those lists, you list the prime factor with the smallest exponent that they have in common. So if they have a prime factor of 3 in common, you're going to list it with the smallest numbers of 3s that each of them have. Kind of like what we were doing when we were pulling things out over here, actually, right on the board. And we're factoring that number out, the question that Emily had at the very beginning. That's actually a lot of what we're doing. What do they have in common? Oh, look, they have a 2 in common. Well, this one has 3 2s and this one has 5 2s. How many do they have in common? 3 2s, because they both have at least 3. And then the last thing, and you do it for all of the primes that they have, and then the last thing that you do is you actually multiply the results together to get the prime, or the greatest common divisor with the prime factors. Honestly, this makes more sense to do when the numbers get larger. You can do it for smaller numbers, that's fine. It works very quickly and easily, but it's really nice when you do it with larger numbers because it breaks them down much more quickly than listing out all of the divisors that the other method would have. So let me go through this one with you. We've got an example with the numbers 400 and 306. Now, I was last class or 2 classes ago, we learned about factor trees and we learned about the division ladder. Do you guys remember that? I'm going to use the division ladder just because that's probably the one you're less familiar with, and so we'll get some more practice with that. Our first number is 400. If you'll remember, the division ladder says we divide by the lowest prime number possible, which would be 2, and that would give me 200. And we do it again if possible, and it is. So I get 100. And again if possible, and I get 50. And again if possible, and I get 25, and it's no longer possible. And then we would say the next prime number would be 3. Will 3 divide 25? No. The next prime number would be 5, and 5 will work. So the prime factorization here has 2s and 5s. How many 2s do you see? I got 4. Is 4 what you guys have? Yeah. Okay. So this is 2 to the 4th. And how many 5s do you see? 2. So this is 2 to the 4th, 5 squared, just for the number 400. We'll do the same thing with the number 360. So we'll divide it by 2 to get what? 180. Divided by 2 to get what? 90. Divided by 2 gives me 45. Okay, will 3 divide that? That's my next prime. Yes, it will, actually. 4 plus 5 is 9, and 9 is divisible by 3, so 45 is as well. What is 45 divided by 3? 15 is correct. Will 3 divide 15? Yep. So we'll do it again. And then that leaves me with 5, which is a prime. So we stop there. So now I have 2s, 3s, and 5s. I have 2, 3, and 5. How many 2s? 3. How many 3s? 2. And how many 5s? Just 1. Okay, so this is like step 1 of this process. Got to get them all into prime factors. So coming over here, that was step 1 taken care of. Step 2 says to find the prime factors that are in both of those numbers. So if we look at these right here, what do they have in common? Bases. What bases do they have in common? 2 and 5. How many 2's do they have in common? 3. There are 4 of them here, there are 3 of them here, so they at least have 3 on each of them, so this is 2 cubed. How many 5's do they have in common? 1. There's 2 here, there's 1 here, that means that the second one only has 1 of them in there. This is 5 to the 1. And we're going to multiply this out. So what is 2 cubed? 8. And 8 times 5 is 40. So our GCD is 40. And it wouldn't be a bad idea to actually look at the numbers you started with and make sure it really divides it. I mean, I can't guarantee at this point that it's the greatest common divisor. My other work shows that it should be. But I can check at least real quick that it divides it. Will 400 be divisible by 40? Yeah. Will 360 be divisible by 40? Yes, it will. It's 90. So, or 9. Good. Good, good. All right, so is this method familiar to you? Not necessarily the division, how I did it, but how you look at which ones are in there. This is usually the one that people have seen the most frequently. Emily? They don't affect the greatest common divisor. We will do things with it when we get to least common multiple. But for the greatest common divisor, they don't affect what the answer is for this. All right, the next method is my favorite method, okay? It's called division by primes, and it has a lot of what this method has in it, but it does it faster. And I don't know about you, but anytime I can save some time doing something, well, maybe not any time, but many times, I like that idea. Okay, my time is worth something, and so I like this method because it saves some time. Division by primes. We write the numbers in a row, and we divide each of the numbers by a common prime factor. And we repeat that. We keep dividing by a common prime factor until no other common factors can be found. The GCD is the product of the primes that we divided by. I'd like to go back just to show you how much quicker the last one would have been if I did this method, but we'll do the practice problem we're supposed to do, the one that's in the notes first, okay? So let me go through this one with you. We have the numbers 410 and 360. The first thing says to write them on a line, like write them beside each other. 410, 360. And we are going to divide by the least prime they have in common. So what is the smallest prime number that divides both of these? 2. All right, good. So what is 410 divided by 2? 205. And how about 360 divided by 2? 180. Will 2 divide both of those numbers again? No. Okay, so let's go to the next prime factor, 3. Will 3 divide both of those numbers? No. Will 5 divide both of those numbers? Yes. So what is 205 divided by 5? 41. And what is 180 divided by 5? 36. Okay, now there's 2 ways right now that you can know you're done dividing. The first way is that you might look at 41 and recognize 41's prime. And if you do that, that's great, you'll know you're done. The second way that you might want to look at this to decide if you're done is to remember that we're doing our divisions in order. I've already tried 2 and I ran out of possibilities. They're not both divisible by 2. I already tried 3, none of it was divisible by 3. I already did 5, and now I know looking at 41 and 36, 5 doesn't work anymore, right? And the next prime number would be 7, but once I get to 7, I'm more than square root of the way to 36. Do you remember when we were looking at prime factors and we said if you take the square root, it tells you how far you have to do the division by? 36 square rooted is 6, right? So I shouldn't have to go up beyond the number 6 to keep dividing this. It isn't necessary. So I'm done. Okay, so 2 different ways to sort of visually see that you're done. So the answer then is the product of the numbers I divided by. So the GCD here is 2 times 5, which of course is 10. Does 10 divide both the numbers that we started with? It does. Okay, so let's actually go back now to the other one that I did so I can show you how it looks different when I use division of primes with those numbers I had before. We would do 400 and 360, and we would divide them both by what number to start with? 2. So put down, if you're writing this back on the page before, write yourself a note so that you don't confuse the issue. This is division by primes. And this method over here was prime factorization. Okay, that gives me 200 and 180, right? Do those divide by both by 2 again? Yep. 190. Will 2 work again? Yep. I now am at 50 and 45. Will 2 work again? No. Will 3 work for both of them? No. Will 5 work for both of them? Yes. So if I divide by 5, I have 10 and 9, right? Are 10 and 9 divisible by anything in common? No. They're too close together for one, right? I mean, they're too close together, but 10 is 2 and 5, 9 is 3 and 3, we're done. So the solution is the product of these numbers. 2 times 2 times 2 times 5. That's 40. We got that before. But it's less work because I don't really even care what happened at the end of the 10 and the 9 and what those were left with. I simply care that I found out everything they had in common. All right, there's one last algorithm. This is the one that is least likely for you to have seen. I'm sorry, Emily, do you have a question?
I didn't get the last one for the
Here? Product. Okay, sorry about that. All right, the last algorithm is the one that you've least likely to have seen. I will tell you where I saw it the first time. The first time I saw it was in a GT program. Do you guys everybody know what GT is? Like a gifted and talented program. And so it was one of those kind of cool trick things that they just don't have time to teach you in schools kind of stuff. And so we did it inside of that environment. There are textbooks, however, that use this as one of their methods as well. So I want to make sure that you're familiar with it. The Euclidean algorithm divides the larger number by the smaller one. And then you divide the previous divisor by the remainder. You keep repeating this till you get a remainder of 0. And the last divisor is the GCD. Highlight this one for me, because that's where people sometimes, they get all the way to the end and then they don't know what their answer was. It's the divisor. The last divisor, the thing you divided by, is the GCD. It isn't a terribly complicated thing to do, but it's definitely not one of those I see why this works kind of things on the surface. All right? So let me show you how we do it. We're going to use the numbers this time of 72 and 54. I'm sorry, 72 and 126. All right, so you're going to divide the larger number, that would be 126, by the smaller one, that's 72. So how many times will 72 go into 126? Just once. And then if I subtract, what do I get when I take 126 minus 72? 54. You heard me say the number 54 before. That's where I was getting it. All right, then these are the two numbers that you're concerned with. The remainder and what you originally divided by. So your remainder becomes the divisor, 54. And what you divided by, originally 72, becomes the dividend. And you do it again. How many times will 54 go into 72? Just once. The answer is not always just once. This one just happens to be, so if you're thinking like that always is going to be one, it's not. 72 minus 54 is 18. Okay, we're going to do it one more time. This 18 becomes the divisor. And what will I be dividing? The 54. How many times will 18 go into 54? It's actually 3 times, and 3 times 18 is actually 54. So at this point, I get a remainder. The remainder of 0 tells me to stop here. And then the last number I divided by is the GCD. So my GCD is 18. Since we have a few minutes left, let's go back and take that same example with the 400 and the 360. I'll just do it on this screen right here and do this process and see it work again, okay? So I'm going to take the numbers 400 and 360, and I'm going to divide the larger number, that's 400, by the smaller. So how many times will 360 go into 400? Once. So what is 400 minus 360? 40. The 40 becomes my divisor, and it's dividing 360, right? How many times will 40 go into 360? 9. 9 times 40 would be 360, giving me a remainder of 0. 0 tells me to stop here. And it tells me that the divisor I last divided by was the GCD. So the GCD is 40. Ariel?
Are you always going to get to a 0?
Yes, always. Now, it's possible that you don't get to a 0 until you end up at the very end dividing by 1. Like if they were relatively prime, you might have to all the way get down to 1 before it happens. I don't know that there's any case in your homework or anything that that's true for, but in theory, you could have that happen. Now, as awkward maybe as this process feels like, or is sort of veiled as to why it's working perhaps, it was really fast with that particular problem, wasn't it? It was probably the fastest way we just did the 400 and the 360. Now, in your homework, you don't have to start the homework if you don't want to. We're not done with this section. But in your homework, as you're looking at GCD problems, sometimes they'll tell you a method and sometimes they won't. So if they tell you a method, please use the method that they specify. If they don't specify for you, you can use whatever you'd like. Do make sure that you're comfortable with the other methods, though. Practice them, because when you get to the test, I'm more likely to tell you what to use than to give you flexibility, because I do want to make sure that you are familiar with more than one way of doing this particular kind of problem, okay?